Okay, why don't we get started? So as I mentioned on Friday, we would start with this problem here. And let's look through and walk through it and so we can gather the information that we need. So we'll consider a tight home that is 300 cubic meters in volume. We have an air exchange rate of 0.2 air changes per hour. The only source of carbon monoxide in the home is the gas range. The ambient concentration of carbon monoxide is 0. The oven emits carbon monoxide at a rate of 1900 milligrams per hour, and the burners each release carbon monoxide at a rate of 1840 milligrams per hour. So we'll create the scenario where we have no carbon monoxide in the home at 6 p.m. So we come home from class, work, there's no carbon monoxide in the house. We make dinner, so we turn on the oven and 2 burners. And we're going to turn this on for 1 hour. And the question is then, what is the concentration of carbon monoxide 1 hour later? Let's look at this in terms of mass balance, but in terms of words. So as we've stated before, we can write a mass balance equation that the rate of change in mass in the system is equal to the rate of change in mass entering, mass rate entering, minus the mass rate leaving, minus the mass rate of decay. So we can write this as the change in mass with respect to time. In terms of mass entering, we have mass in from infiltration. We have mass in from whatever internal sources we have. So in this case, the gas oven range, so gas oven and burners. We have mass leaving through exfiltration, and we're lumping here natural ventilation, forced ventilation, and infiltration. So, and we have the mass rate due to decay. Now, if volume is constant, I can write this expression as we know mass is equal to concentration times volume. So volume is constant. Volume is out of the differential, so we have change in concentration with respect to time times the volume. We can describe the mass in using the terminology that we developed on Friday times the concentration, the ambient concentration. So that's the concentration from the outside entering the building times I times V. Typically, we'll use just a capital S for the source term minus C out I V minus, and if we have a first order expression, we can write this mass rate of decay as the rate constant, which has units of inverse time, times the concentration, and this is concentration out, times the volume. Now we said also that the concentration inside, and I'll just refer to this as the reactor, the concentration in the reactor is equal to the concentration leaving the reactor when what conditions are applicable? when is the concentration of in the reactor equal to the concentration leaving the reactor? If it's steady state, then this term here is equal to 0. So steady state means that the change in mass with respect to time is equal to 0. So under what conditions will the concentration of the reactor equal the concentration leaving the reactor? When we have a continuously stirred tank reactor or a completely mixed tank reactor. The assumption here is we have complete mixing. And if you think of this, here's our house. Okay, so we're looking at the kitchen. If I measure the concentration of carbon monoxide at any point in this home, those concentrations will be equal, and it's the same as what's leaving through the ventilation system, through a window, open door, etc. And so we're assuming we have a completely mixed. The general solution for this equation here, where K is equal to 0, so where we have a conservative pollutant, so K is equal to 0, we can differentiate this expression here. So it's not, this is not written for steady state. So the concentration is changing with time. It's a function of time. It's a function of the source term, the ambient air concentration, the infiltration rate, and the initial concentration. So if you think here, if we were to plot concentration as a function of time, it's an exponential plot. So what we will see is something that looks like this. So the concentration changes with time, and it's an exponential function. If, on the other hand, we start at a higher concentration, we'll still see an exponential plot. It's just going to start at some other non-zero concentration. Any questions about these terms? So for the previous problem, S is equal to the 1900 milligrams per hour plus 1840 times 2, because we have 2 burners and an oven. The volume is equal to what? For the problem that we're working on, 300 cubic meters. The time that we're asked to calculate the concentration at is equal to, we turn on the oven at 6 p.m. We're asked to determine the concentration at 7 p.m. So T is equal to 1 hour, good. C sub A is equal to
0.
0, good. I is equal to 0.2 air changes per hour. So the units are inverse hours. And the concentration at time 0 is equal to 0. So given that, we can substitute that the concentration at 1 hour is equal to 1900 plus 2 times 1840, and that's milligrams per hour, divide by 0.2 inverse hours, and the volume, 300 cubic meters, and that is 1 minus e to the minus 0.2 inverse hours times 1 hour, and that is equal to 16.85 milligrams per meter cubed. Inverse hours cancel. Notice inverse hours and hours cancel, so make sure your units are consistent. And we now have a concentration for carbon monoxide after 1 hour. And if I plot this, okay, this is what the curve would look like. It doesn't look exponential. It actually is. And you can see how the concentration of carbon monoxide is increasing as a function of time. Now, if I turn off the stove at 7 p.m., sit down, have dinner, don't turn on the stove again until maybe dinner time the next day, what would I expect to be the profile of my carbon monoxide concentration? So at this point in time, I'm going to turn off the oven and the range. What happens to the concentration?
It would flatten out.
Okay. Let's look back at this equation here. So now what happens to this S term here? I turn off the oven, I turn off the range. It becomes 0, exactly. So this becomes 0 now when I turn off the oven. C sub A becomes 0. C sub 0 is that 16.8 milligrams per liter. So what happens to the concentration now as a function of time? What happens to this whole term here? Once I turn off the oven, what happens to this whole term? It all becomes 0, doesn't it? So then the only thing that matters is this portion of the equation. So what happens? My concentration decreases as a function of time, and it decreases exponentially. So now when I shut off the stove, this term, as I mentioned, all becomes 0. This term is now the only relevant term. So let's calculate concentration 10 hours later. So C at 10 hours after I've shut off the stove is equal to 16.85 milligrams per cubic meter times e to the minus 2 inverse hours times 10 hours, and that is equal to 2.28 milligrams per cubic meter. So there's still significant carbon monoxide in the air even 10 hours later. So now we've assumed here, remember, we've assumed that carbon monoxide is conservative, which means that K is equal to 0. We're assuming that it's non-reactive. And so the concentration is decreasing, and it's decreasing exponentially. And it would look like this. So you can see we started out at 16.85, and you can see we're at 2.28 after 10 hours. And you can see even after 20 hours, we have measurable carbon monoxide under this scenario. Questions about this problem? So let's look at radon. Radon is a colorless, tasteless, odorless gas. It is naturally occurring, and roughly half of our exposure to radiation actually comes from radon. It is found in nearly all soils. It is also in building materials made from geological materials, so it can be found in concrete, for instance. And it's formed from the decay of uranium. So uranium, it's naturally occurring. It decays to form radium which then decays to form radon, which decays to form polonium. So this is the decay sequence of these elements, isotopes. I've also given you the half-life. So you can see the half-life of uranium is on the order of 10 to the 9 years. On the other hand, the half-life of radon is on the order of 4 days. So it's decaying much more rapidly than is uranium. When we measure radiation, the older unit that was used is a curie, and 1 curie is the quantity of unstable atoms whose frequency of decay is 3.7 times 10 to the 10 disintegrations per second. So if you were at a Geiger counter and you're measuring disintegrations, then you would, 1 curie would be that amount of material for which you recorded 3.7 times 10 to the 10 disintegrations per second. Becquerel is the newer unit, and it is the quantity of atom whose frequency of decay is 1 disintegration per second. And a becquerel is 2.7 times 10 to the minus 11. It's the inverse of this value here, curies. To give you a sense of kind of the scale of what we're talking about, the common radioisotopes, the first 4 are the ones that I've mentioned before in the decay of uranium-238. So the mass equaling 1 curie of activity, for instance, for uranium is roughly 3 million grams. On the other hand, radium is 1 gram. Radon is on the order of 10 to the minus 6. So now we're looking at about 6 micrograms of material would have 1 curie of activity. Polonium is about 2.2 times 10 to the minus 4, and cobalt-60 is about 9 times 10 to the minus 4. Notice here the relationship between the mass equaling 1 curie of activity and the half-life. The greater the mass, the greater the half-life. And you can see that here where I've plotted half-life versus the mass equaling 1 curie. Some discrepancy down here, but you can see that there is a relationship. The greater the half-life, the more mass we need in order to achieve 1 curie. We typically measure radon in units of picocuries per liter. So it's liter of air. Almost every other case we use cubic meters, but picocuries per liter is the common set of units for radon. And they haven't switched to becquerels. We've kept with curies. To give you a sense of the importance of this issue, at concentrations greater than 4 picocuries per liter, EPA recommends that some mitigation activity be accomplished in order to reduce the radon levels in the indoor air. And you can see there's a significant portion of the US that is bright red. And these are the areas where it's common to find indoor radon levels that are greater than that 4 picocuries per liter. So these are areas where putting in a mitigation system is often needed. If you buy a house in any one of these areas, my advice is have the radon testing done to determine whether or not you need a radon mitigation system in the home. If we look at Michigan, you can see all of the southernmost counties in Michigan are red. So these are areas where the concentrations are great, where well, typical concentrations in indoor air will be greater than 4 picocurie. So you really want to make sure if you're buying a house in these regions, in these counties, have radon testing done. If you're buying a house in any of the orange areas, I'd also recommend it. We have a radon mitigation. We're right somewhere in here. And yes, we have a radon mitigation system. It was put in by the previous owners, and we maintain it in order to make sure that the radon levels in the home are well below, ideally below the 2 picocurie per liter. And the reason we mitigate for radon is because it can cause lung cancer. It's actually the second most common cause of lung cancer after smoking. And smokers are more at risk than non-smokers. I've included these tables. I'm not going to spend a lot of time here, but gives you some sense of the risk. So for instance, at 4 picocuries, the lifetime additional risk for exposure to radon would be 62 out of 1,000. So the risk, that's the additional risk due to exposure due to radon, and that's roughly 5 times the risk of dying in a car crash. And EPA recommends that at that level, you fix your home. If we look at non-smokers, the risk here is only about 7 out of 1,000. So that's the additional risk due to the exposure. And it's the risk of dying in a car crash, not 5 times that. And again, you're recommended to fix your home. How does radon get into the home? Okay, so if we have a basement or even a slab, and we have uranium-238, even in small quantities, in that geological material, that radon decays to form, that uranium decays to form radon. And then that radon, because it's a gas, can permeate through any cracks in the floor, through construction joints, through any cracks in the wall, can around any service pipes. So if we have our sewer pipe coming in, gravel around that, it can permeate around and then into the home that way. Any cavities inside the walls. So that radon then gets into the house. We talked about the stack effect, especially in winter, where warm air rises. So what happens? That warm air rises, pulls the cold air from the basement, and pulls more radon into the home. So let's look at a problem where we calculate, in this case, we're going to calculate the steady state concentration of radon. So we'll assume that the soil under a single-story house is emitting 1 picocurie per meter squared per second. So that's that meter squared is the area. We're going to assume that all of this radon finds its way through the floor into the house. The house has 250 square meters of floor space. It averages a ceiling height of 2 meters, and we have an air exchange rate of 0.9 air changes per hour. And radon decays according to first order kinetics with a rate constant of 7.6 times 10 to the minus 3 inverse hours. What we're asked to do is to calculate the steady state concentration. We'll assume that the concentration of radon in the ambient air is 0. So again, let's initially just draw a picture. I'm going to draw this so that we have an area. So what we've said is that the radon is emitting, or the geological materials are emitting radon at a rate of 1.0 picocuries per meter squared per second. So this is our source term. The area, floor area, is 250 meters squared. The ceiling height is 2.6 meters. So our volume is equal to 250 meters squared times 2.6 meters. K is equal to 7.6 times 10 to the minus 3 inverse hours. C sub A is equal to, what is C sub A equal to? 0. I is equal to 0.9 inverse hours. And we're asked for the steady state concentration. The more general form of our mass balance expression is here. Notice we've added the K term. So we've added a K term in the numerator here. We've added a K term in the exponential of both C sub 0 and in this term here. So at steady state, the change in mass with respect to time is equal to 0. For those of you that haven't taken 483 yet, we will use this same set of notation in 483. For those of you that haven't taken the FE, these types of problems are on the FE. So I've written the expression out here with the terms we've used. Notice this is equal to 0. This term we said was equal to 0 because C sub A is equal to 0. So therefore the entire term is equal to 0. And we can rearrange this part of the equation is equal to 0 so that we have an equation for the steady state that says that is equal to, in this case, this is 0. It's equal to S over V times I plus K. So that's our steady state concentration. We can also obtain it here by if T approaches infinity. If T approaches infinity, this term approaches what?
0.
0. Exactly. So in steady state, this term becomes 0. This term here, so this term right here, also approaches what?
0.
0. In which case then this equation here is the same equation we have down here. And if we solve this, so if we substitute and we solve for this, we will end up with 1.5 times 10 to the 3 picocuries per meter cubed. Notice it's in meters cubed because volume is in meters cubed, which is 1.5 picocuries per liter. So this is just substituting in the equation, the values that we have here. And so notice since volume is in meters cubed, it's picocuries per meter cubed, and then we can convert to picocuries per liter. So do we need to do anything? Probably not in this case. If we did, then we can look at mitigating these risks. There are a number of ways that you can do that. You can seal the cracks and openings in the basement, so you try and prevent any infiltration of the radon from the soil material or the geological material into the house. There are a number of mitigation systems that essentially pull radon from the subbasement and pipe it actually to the roof. So this is what we have in our house. There's a sump pump, which is a sump that's not pumping water, it's pumping gas. So what it's doing is it's taking, it's pulling the air from the subfloor so that it permeates and basically goes up the pipe to the roof, and it's vented outside. The link here is actually a link from the show This Old House, and they actually go through the whole process of installing a radon mitigation system. So if you're interested in that, like I said, if you're thinking about buying a house in any of those areas that were red, just for your own edification, I would watch it just so that you have some sense of what you might want to do if you're in that situation. And this is just some figures showing the mitigation system. Basically, there's a suction pit, so that's a sump that I talked about. There's a YouTube manometer to make sure that the system is working. The radon tag is put in by the installer. We monitor radon at least it's actually monitored regularly, and then we do, about every couple of years, we do an additional check to make sure that the radon levels are acceptable in the home, especially in the basement. And then you can see here how the radon is vented outside. Any questions? We're got about 6 minutes. Happy to answer any questions that you have.